Hello there, welcome back to Blockchain Buzz Africa. If you're new to the channel, my name is Henry, and at PBA our goal is to help you navigate through the world of Web3 and blockchain. So whether you are a blockchain enthusiast or just starting out, we've got you covered with the latest tips, news and insights. In this episode, we are going to have a masterclass on cryptography and why it's the backbone of blockchain. So if you have not yet subscribed to the channel, kindly hit the subscribe button and turn the notifications on so that you don't miss on upcoming content. Let's get started. Cryptography Masterclass. So we are going to look at blockchain. To understand how blockchains work, let's start off with some high-level questions. What is the purpose of blockchain? The purpose of blockchain is to have a network of computers agree upon a common state of data. Plain and simple. So any person or organization should be able to participate in this process. No person or organization should be able to control this process. Generally, the term consensus is used to describe a network coming to an agreement on the state of the data. You will hear this word quite often in regards to blockchain. So, just to continue, a continuation of the same, blockchain was invented to solve the problem of trust, to create a system that is completely neutral and resistant to any censorship or bribe. Let's take a look at smart contract blockchains. Smart contract blockchains provide developers with a way to decentralize where the code runs. In this way, code can truly become a public resource. This means code can run without any direct ownership, making it censorship resistant and transparently verifiable. One important point to note is that decentralization is not about the code itself, but how the code is executed. So let's dive into cryptographic hash functions. A hash function is a function which takes in an input of any size and turns it into a fixed size output. Let's imagine a hash function that takes an input of any size and returns a fixed 32-byte output. So below is a diagram that shows different inputs and the outputs in terms of their sizes. So for instance, an input of 52, which is actually 8 bytes input size, the output is 0x1 in hex and the output size is 32 bytes. So you can see on the diagram we have different types of input. We have a number, we have a string, we have an image, and we have an MP4, but they all map to the same output size of 32 bytes. So let's look at some of the characteristics of hash functions. One of the characteristics of hash functions is they are deterministic in nature. So this means one specific input always maps to the same specific output. Another characteristic is pseudorandom. It is not possible to guess the output based on output of similar inputs. Fast to compute. It must be a quick calculation for a computer. One way. If someone gives you a new output, you could not determine an input without guessing. Collision resistant. The chance of a collision should be infinitely small. So these are some of the characteristics of hash functions. With a secure cryptographic hash function, you can create a unique fixed size representation of an input regardless of its size. For blockchain, this feature is critically important for saving space. In some cases, blockchains and smart contracts will need to store an input. They can just store the hash output instead. So cryptographic hash functions will be super important for the first successful blockchain consensus mechanism, which we are going to talk about in a moment, which is proof of work. Some of the cryptographic hash functions we know today are like SHA-256, which are one-way function, So this means that if you have the input, it's relatively trivial to find the output. On the other hand, if you have the output, it is infeasible to find the input. Let's dive deeper into public key cryptography and take a look at the history of cryptography. It's helpful to look back at the study of cryptography over the years to understand where and when digital signatures came into play. So, historically, up to until 1970s, cryptography was the study of encrypting messages so that they could not be decrypted even if intercepted. Cryptography was used for passing important secrets, especially within the military. The sender will take their message and pass it through a function to create an encrypted output. This could be something as simple as moving each character in a string down the position in the alphabet. For instance, quote-unquote ABC becomes BCD. This function is not particularly difficult to crack, especially once you know its secret. As cryptography advanced over the years, more complex functions were introduced to hide messages better. One important leap forward was the idea of a secret key. If two parties can meet prior to their exchange of messages, they both can come to an agreement upon a particular key. This key plus a function like the alphabet shift mentioned above could be used together to create a more secure encryption. So, having keys on both sides of a message is considered symmetric key cryptography. Let's take a look at personal computing. As mentioned above, the state-of-the-art cryptography had been increasingly complex versions of symmetric key cryptography. The objective of the game was to never let your adversary have your key. And of course, in military situations, countries were doing everything in their power to break your code. So, with the advent of personal computing on the horizon, some cryptographers started to think outside the box. People who want to be able to communicate with each other securely without having to worry about eavesdroppers. Of course, they could meet somewhere in person and exchange keys anytime people wanted to talk securely, but this seemed a bit old-fashioned. This was a tough problem. We got cryptographers thinking, how could two parties communicate securely without having met beforehand to exchange keys? Was this even possible? That was the question. In 1976, Whitfield Diffie proposed an idea. What if there was a public key? Many established cryptographers dismissed this idea out of hand. After all, the whole purpose of an encryption key was to keep it private. As it turns out, a public key introduced some extremely important cryptography properties. Take a minute to walk through this thought process experiment conceptually with me. You ready? Let's start the thought experiment. So, let's say there is a private key that can decrypt messages from a public key and vice versa. Each key is the only key that can decrypt a message encrypted by the other key. Now imagine Bob has declared a public key far and wide as the key that identifies him. Bob will keep a private key that corresponds to his public key. When he uses his private key to encrypt a message, he can share it publicly to be decrypted using his public key. Upon decrypting his message, we can say beyond the shadow of a doubt that only Bob could have written this message. The only key that could have encrypted the message is the corresponding private key which only Bob has access to. In practice, this will create an unforgettable digital signatures for Bob. On the flip side, what if the message was encrypted using Bob's public key? Of course, anyone can do this since Bob's public key is available to everyone. The benefit comes in that only Bob can decrypt the message in the way a friend Bob's can write a message that can only be read by Bob. They could send it through any network regardless of its security, so as long as it reaches Bob. they could rest assured that nobody would be able to decrypt the message except for Bob. This was the insight that struck Whitford Diffel in 1976. The only problem was he didn't have any practical way to make this happen. He had a concept, but he did not have a mathematical function with these properties. Diffel will work with both Martin Hellman and Ralph Mikl in search for such a system. Note, it's this kind of mind-blowing to think that this invention started with a concept before finding a mathematical function that could satisfy these properties. As opposed to the encryption techniques method in the above section, public key cryptography is considered asymmetric encryption in that only one party has access to the private key. Let's talk about RSA and ECDSA. Today, both RSA and ECDSA are two popularly used algorithms for public key cryptography. The RSA algorithm is based on the idea that it's very easy to find the product of two prime numbers, yet extremely difficult to factor out those two prime numbers if you have the product. ECDSA, you can actually see that the ECDSA algorithm uses elliptic curves. It can provide the same level of security as the public key algorithm with similar key sizes, which is the reason it's become quite popular. It is the digital signatures algorithm used by Bitcoin, especially the SEPT 256K1 curve. The mathematics behind these algorithms can be quite difficult to wrap your brain about. How difficult the RSA algorithm is to decrypt is still unsolved mystery in computer science. It is assumed it can only be decrypted in exponential time relative to the size of the input, which essentially boils down to a brute force attack of random guessing at the key. Let's look up on proof of work and mining. Blockchain networks like Ethereum are essentially distributed and decentralized databases consisting of many nodes, fancy name for computers. In a decentralized environment, these are the common issues are: how do all nodes agree on the current and the future state of user account balances and contract interaction is? Who gets to add new blocks or transactions to a chain? How do we know any blocks added are valid? How the heck are all of these things coordinated without any central actor in place? The answer is consensus mechanism. Yes, you thought just right. Let's take a look at consensus mechanisms. Consensus mechanism actually means coming to an actual general agreement. Blockchain consensus typically means at least 51% of the nodes are in agreement over the current global state of the network. Consensus mechanisms end up simply being rules that describe a distributed decentralized blockchain network that follows in order to stay in agreement over what is considered valid. Remember that consensus mechanisms are interchangeable, and there are many out there that we yet are to cover, like proof of stake. The main consensus rules of proof of work typically looks like religious commandments. You cannot double spend. The longest chain will be the one the rest of the nodes accept as the one true chain, determined by a chain cumulative work, also known as Nakamoto consensus. So, Bitcoin, being a blockchain network, uses a consensus mechanism called proof of work. Ethereum was previously using proof of work but has since moved to proof of stake. We will not be covering proof of stake here for now, but in the meantime, you can learn more about this transition here. Let's take a look at proof of work. Proof of work is the consensus mechanism that allows decentralized networks like Bitcoin and previously Ethereum to come to consensus and agree on things like account balances and order of transactions. This prevents users from double spending their coins and ensure that everyone is following the rules, making proof-of-work-based networks resistant to attack. The consensus mechanism ends up providing security to a blockchain network just because it demands that everyone follows the consensus rules if they want to participate. In proof-of-work, mining is the work itself. So let's look at mining. Mining is the process of creating a block of transactions to be added to a blockchain. Plain and simple. But how does that tie in a proof of work? Well, proof of work will just as well be called proof of mining. In proof of work consensus, nodes, aka computers in the network, continuously attempt to extend the chain with new blocks. These are the miners, nodes that contain mining software. Miners are in charge of extending a block by adding blocks that contain valid transactions. In order to add a block, the network will ask the miner to sue for their proof of work. A proof of work-based system will typically require miners to produce an output in a very difficult to get target range. A valid proof of work will currently look like 13 zeros as shown on the diagram. So, how the heck does a miner get an output like this right? Well, the automated mining software has one job: take a piece of data, e.g. the previous block header, plus new transactions to add to a chain and hash it. If the hash output is below a target difficulty, then the miner has found the answer to the puzzle, a valid proof of work. Mining. Note: the proof of work shown above has 19 leading zeros. That's a ton. Since the range of each possible character per space is in hexadecimal, this means that we can have 1/16 character possibilities per space. The hash outputs of SHA-256 are in hexadecimal, which means that we have 1/16 possible characters per space. AF in letters and 0 to 9 in decimals equals to 16 total possibilities. This means finding one 32-byte SHA-256 output that is just one leading zero will take an average of 16 tries. So, with any random input, how many tries did it take for you to find out an output with one leading zeros, considering the link? The thing is, once we start adding more difficulty, things start to get more difficult. Finding an output with two leading zeros increases the average attempts to 256, 16 possible characters in the first spot, multiplied by 16 possible characters in the second spot. Finding 19 leading zeros will take an average of that huge number attempts. Here's what proof of work mining algorithms look like. Take current block's header, add mempool transactions. Append a noun starting at noun 0. Hash the data from, this case, process 1. Check hash versus the target difficulty provided by the protocol. If the hash is less than the target, puzzle is solved. Get rewarded. Else, you adjust the nouns to 2 to 1 from 0 and you begin the process entirely until the required target. Proof of work networks will typically have some sort of a target difficulty. In order for a miner to add a block, they must find a proof of work lower than the network target difficulty. It's basically the network saying, if you want to add a new block, you must provide a proof of work with 12 leading zeros. The way the math works, finding such difficulty to find output is proof enough that the miner experienced considerable resources to secure the network. There is no way to cheat the system. You either have a valid proof of work or you don't. So the miner nodes in a proof of work network will perform the algorithm regularly. This gives the network a way to recognize the true state and validity of proposed transactions via following the consensus rules. As long as the majority of the nodes of the network follow the consensus rules, why do miners expend resources to secure proof of blockchain network like Ethereum or Bitcoin? In exchange for the large amounts of energy and hardware upkeep required to run mining software, miners receive currency as a reward. If the consensus rules are followed, making a secure network, miners get paid. In conclusion, in proof of work, miners must present a proof in the form of a hash output of a valid input data that they can expend energy in order to successfully mine a block and have it extend blockchain. So that marks the end of our cryptography masterclass. Hopefully you are able to learn something about cryptography. Until next time, goodbye.